So, starting our next lesson, we are going over transformations. So, on the notes I just handed out to you, the first ones that they bring up, or the first thing we're going to do is define transformations. So, here's what you need to copy down on that definition line. A transformation is just mapping. It's going to be on a plane, and you're mapping a transformation. If you have some pre-image, it should have some point exactly like it in your image, and each image point should have had some pre-image point. So what I mean by that is, back when we were when we were making constructions, like congruent line segments, whenever we had some line AB and they asked us to reconstruct a congruent segment to AB, we redrew the exact same thing, so we named it like A prime and B prime, right? So we were reconstructing something that was still those points, just moving it somewhere else. So that's similar to what we're going to be doing here. In your figure, the new figure is your image, while the original one, the one they gave you, is going to be your pre-image. Okay? Or your original is like the A and B, and your image is going to be your A prime, B prime, the new thing that you make. All right? So, then they next are going to list a few of the types of transformations that we could see. And they have all 4 of them written out there with pictures as examples of each kind, right? Everybody get the definition? Okay. All right, next slide then. Okay, so these are the ones that are on your paper. The first is dilations. And dilations, it says the figure is either going to be enlarged or reduced. All that means is that the size is going to change. So either it starts out as some small square and makes a bigger square, the exact same measurements, just move bigger on a scale factor, or maybe it starts big and gets smaller. Still should be the exact same shape, it's just going to get bigger or smaller. And this is the picture that they have drawn on your paper. So see, it started out as this oval, exact same shape, just got bigger on some scale. All right, and then we have rotation. All right, rotation just means the figure is being turned. So nothing should change about whatever it is you're turning, except the fact that it will turn. So like if I was to rotate this piece of paper, all I'm doing is turning. Right? The size of it didn't change. What's on it didn't change. All I did was turn it. Right? And you don't have to just turn it half, like maybe you turn it half of a circle, right? So you could turn it all the way upside down, or 3/4 of the way around. Okay. All right, and then we have translation, which just means that your figure is being slid somewhere. So this is the image that they show you. So if this was my image that I was translating, I could just slide it over here, or slide it up, or down, or over here. Okay. The last type that we're going to talk about here is reflection. Okay, and that just means basically I could flip the figure, or it has some line of symmetry where I could fold it in half and it would still meet back up. Right? That's what's different about these two. This one was here and I turned it here. If I folded those, this one's sideways now, right? It's not the same. This one is still the exact same thing. If this was it gets flipped across. Okay? So if I folded this in half, everything would still meet up. So that's the difference between rotation and reflection. All right. Okay. Next, they have these images drawn for you, and they want you to take a second and identify what type of transformation each one of these pictures shows. So under each image or beside each image, I want you to tell me if it's showing dilation, rotation, translation, or reflection. I'll give you just a second to go through and answer those 4.
100.
Yeah, that's fine. Okay, so on image A, are those still the same shape itself? Yeah, right? It was just here, and then they turned it some, right? So what would that be? Rotation, right? It's still here at this point, it's just been turned, right? This is not reflection because this side is over here, right? If it was reflected, this would have been on the outside, right? So it is just a rotation. All right, B was kind of tricky. What do we put on B? Okay, so if it's reflection, it has to meet up, right? Did you check to see the doors and windows? It's rotated, right? So it was here and it was rotated all the way around. Because if it was reflected, then the door would have been directly across from it. So that one was a little bit tricky if you didn't pay attention to the windows and doors. Okay, and then on image C, what's that one? Right, they just had some figure here where they slid it somewhere else. Good. And then figure D. Right. If I folded that in half, everything would meet up exactly. So that one is reflection. Good. Okay? All right. All right, then we have isometry. So its definition is, again, it's in a plane. And this is just a transformation that's going to map every segment to some congruent segment. This can also be called a congruence transformation. So, key thing here is congruent, which means same size, same shape, right? So it can't get any bigger or smaller and still be congruent. So one of those that we talked about up there wouldn't show congruency, right? One of the 4 types we talked about. Okay, so once we have our definition written down, they have some examples here. Okay, they want you to go in and first decide what type each one is showing. Dilation, rotation, translation, reflection. And then you need to determine whether that picture shows isometry, which would mean got to be congruent. Right? Same size, same shape. Okay. So on A, are those 2 figures the same size? No, so what happened? What'd they do? Dilation. And if they're not the same size, are they congruent? No. So these would not show it. This is just dilation. Okay. On B, are those the same size? Yeah. Yes, it is reflection, right? Because if I was to fold it right there where they touch, they would meet up exactly. Good. And since they are the same size and shape, it does show isometry. All right. Okay, what are they showing us on C? Reflection again. So would that also show it? Good. And what about D, the one with the ants? Dilation. And would those be congruent? No.
Just for the shapes, that's what we got.
Okay. Once you got that, go ahead and turn to the next page. Alright, so now we're going to specifically talk about translations, which is the one we said where we're just sliding, right? Okay, so for translations, Our definition is that it is the result of a movement in one direction. Okay, so on the front page we said it could move over here or maybe move diagonally, right? It's just going to move some way. It's also the end result of two successive reflections. Successive just means one after another, right? And this can be called a composite of reflections. Now, when we're dealing with properties of translations, two things are always going to hold true or preserve. Every time you have a translation, it's going to stay the same shape or size, which would mean stays congruent, right? The original one and the new one, same size, same shape. And their orientation will stay the same. And orientation just means the way it's facing, right? So if it was this piece of paper and I translated it up, it's still facing up and down, right? If I turned this piece of paper, that's no longer translation, that would be rotation, right? So it's got to stay facing the same way that it already was. Okay? We got those? Okay. All right, so when you have some translation, it's just some transformation that we can describe in coordinate notation this way. So what you'll always do is write the original coordinate point, which will just be some x and y value, and then you'll put some arrow here, and in this parenthesis, you will denote whatever change is happening. So if your x is changing, x can only move left and right, okay? So if I add 3, I'm moving to the right. If I subtract 7, moving to the left. Y can move up and down, so whatever number they put in there is telling you to move something up or down. Okay, and we'll just use H and K to denote that, but it could be any number, like I was just saying, plus 3, minus 7, plus 12, minus 6. And like we were just saying, X only moves left and right, so H is going to shift things left and right. And while Y can only move up and down, that means K will just move things up and down. And our H and K could be whatever number the graph is showing. Okay? Everybody got those? Okay, then they give us this drawing over here. Yours is a coordinate grid. I don't know what happens in the squares here. But they have a figure drawn on your paper, and it wants to first know what the given coordinates are. So it wants you to look on your paper and see what coordinate point A is at.
3,
Okay, so that's what I'm going to put in the blank right here. Where is B at? Good. And C? And D? Good. So we have all of our original coordinate points there. And they took those 4 coordinate points, connected them, and made a trapezoid. Right? Okay, on example 1, it's saying that we're going to take our original coordinate point and we're going to increase x by 3, decrease y by 5. When we see that, we should be able to go ahead and just add or subtract that to our coordinate points without having to come over here and count that many spaces. Okay? So if I'm increasing x by 3, and it was already -3, -3 plus 3 is 0. So my A prime coordinate point for x should be 0. I was at 3. I'm subtracting 5. 3 minus 5 is -2. So my A prime should be at 0, -2. Okay. Same thing for B prime. I'm starting at 0. If I move right 3, that's going to end up at, and y is going to become, good. All right. And then my C prime going to work the same way. I was at 1, 1. I'm going to add 3 to this one, subtract 5 from this one. So C prime is, good. Alright, and then there's my D prime as well. Same process. Okay, and then once you have those coordinate points, you can draw those over here on your coordinate grid, and you can see it's the exact same shape as what was already there, right? So it stayed congruent. Did it turn or rotate any? No. So it also held its orientation, which we said those two things had to stay. Got to be the same size, same shape, and it can't turn. All right? Same thing for number 2 here. This one, though, says that we're going to subtract 3 from x and not change the y at all. Okay? So I go back to the original points that were up here. A's original x value was -3. If I move left 3 more spaces, where would I be? -6, and then it said not to change y at all. So A prime would just be -6, 3. Okay? Alright, I'm going to do the exact same thing for my B. So what would this B become? -3. Good. And what about C? So C was 1, right? And it's going to become, what'd you say, -2, 1. Good. Okay, and then D? Good. All right, and then once I have all those written, I can go back and connect them. And again, we can see it's still the exact same shape. It's just been moved over. All right? Okay, so the first one they did, they called each point prime. The second time they did it, double prime. Right? So every time you redo it, you just add a prime to it. For numbers 3 and 4, you can graph those on the second coordinate grid. Okay. On those two, since you are starting on a new coordinate grid, you could just name them A prime and A double prime again, or you could keep adding on. It could be your triple prime, quadruple prime. But we're still starting with those same original coordinate points. Okay. This number 3 says keep x the same, but add 4 to our y values. So what is my A value going to be on number 3, my new A?
7.
Negative, other way around. Okay. Okay, and what would B be? 0, 7, good. And C? Good. And D? Nice. Okay, and once I have all those, I can go over here, draw it on my coordinate grid, and connect them all, and I can see. It's the exact same shape, it's just been translated up. Okay? All right, and then last one, this one says we're going to move left 2 and up 5. Still going back to those original points. Okay? So, what would our A value be for that one? Good. Okay, what would B be? -2, 8. And then C? Nice. And D. Good. All right. And once we have all of our points, we redraw. We can see again, it's just been translated diagonally slightly. All right, but this right here is the notation that we use to show what kind of change is happening. The original coordinate point, draw an arrow to your change. Okay? All right. And now that we've talked about this way to denote our change, there's actually a second way we can write it other than just as coordinate form. The other form is vectors. So once you've got that written, if you will flip over onto the next page. Okay. So our other form, vectors, is a way that we can describe the translation that's happening, so some kind of a movement or shift. And a vector is going to be a quantity that shows both direction and magnitude or size. Okay, it's going to be on some coordinate plane, and it's denoted by an arrow. Does everybody have this? Can I change to the next one? Okay. All right, so this is already typed out on yours. And then they give a drawing to show what they're talking about. So it says that this diagram shows the vector named FG. It starts at F and the arrow goes to G. So when we name it, we're going to name it just like we do our rays that we learned back in 1.5. You always put the end point first and then the other letter with the little arrow above it. Okay. These arrows also show some left or right movement and some up or down movement. For example, this one, if we count on that little grid, we can see that it moved right 5 places and up 3 places. So when I come up with the vector, 5 units to the right is the positive direction, so I'd use a positive 5. 3 up is also positive, so I'd use a positive 3. And it may be kind of difficult to tell. I'm going to have to let me draw on this. Yeah. But this is the symbol. It's not a parenthesis on the outside there. It looks like this. Okay. All right. So now that they gave us an example, on example 3, they want you to name the figure and then draw it or write down what its vector would be. So plug in the right numbers. Okay. So for A, what's my starting point? B. So when I name it, I'm going to name this BC. Very good. With that arrow above it. Okay, and then when we write down the vector, we're going to count. Okay, how many did I move and which direction did I go for left and right? 9 units right, which would be in the positive direction. Good. Okay, and then up or down, how did we move? 2 down. So I'm going to have to put a -2 in that vector. Okay, so this is how we would write that. 9, -2. Okay. On B, how would we name that one? ST. Good. Okay. And then what would be the numbers in our vector? Very good. Yes, since we moved to the left, it is negative. So we put a -8, but this one didn't move up or down any. So 0 for up and down. Okay. All right. On example 4, it says that the vertices of triangle ABC are the points A at 0, 3, B at 2, 4, C at 1, 0, and they want us to translate this triangle using vector 5, -1. So first, you need to plot these 3 points on your coordinate grid. So that's this white triangle that I have already drawn up here. So you need to plot these 3 coordinate points on your grid and label them A, B, C. All right. Oh, like showing how it's going to go. You don't have to. You don't have to because you can count, right? You don't have to draw them. But that's where the vectors would go. So if I have a 5 here, that means I moved where 5? Right, so I'm going to count from point A, 1, 2, 3, 4, 5 places to the right, and -1 means down 1, and that's where my A prime would go. Okay, and then you're going to do the same thing for your B, and the same thing for your C. All right, and what she was talking about were the arrows, were the vectors that you would actually draw in, showing that you went over 5 and down 1. And you can draw your vectors if you'd like between each point. And once we have them drawn, we can then see where A prime, B prime, and C prime would end up. So you could give the coordinate points for those. Okay. All right. In the next set of examples, it says that we're going to describe each translation. In A and B, they want us to describe the translation in coordinate notation. And then for C and D, we're going to describe it in vector notation. Remember, this is vector. Coordinate is our x plus h, y plus k, right? Okay, so here's A and B. These are the ones we're doing in coordinate. Remember, we write the coordinate, the original, which would just be x, y, right? Draw your arrow, and then x plus your h, and then y plus your k, and you plug in those numbers. You tell me what's happening here. Okay. So if I'm moving left 5 units, what am I going to put in there? Minus 5. And down 3 units, I would put, good. So I have my original coordinate point here, x, y. I draw my arrow, x minus 5 to show left 5, y minus 3 to show down 3. So this is our coordinate notation. And B wants the exact same type of notation. So same thing, just change out the numbers. Okay. So B says we went right 6, so what are we going to put in there? Plus 6 and up to plus 2. Good. So there's our coordinate notation for B. Okay. All right, and then C and D want our answers in vector notation, which means we don't put the x and y in there, right? And we don't use parentheses. We use the other symbols. So for C, we're still starting at some original point x, y, but in my vector, what numbers are we going to put? Very good. Okay. And for D, what's that one going to have in the vector? Good. There's our notation for that. Okay, next we are talking about reflections. So reflections are just another type of our transformations. They give us a little drawing here that says that the line M is the line of reflection. That's what we call it, because that's the line we're reflecting across. Okay, so whatever was up here, I reflected it down here. Okay, it says that X is the original, right? We call that the pre-image. There it goes. And X prime is your image. Okay. And P was on the line, so if I folded on that line, P is still just on the line, right? That's what they're saying with P prime. It didn't move because it was on the line, not above or below it. Okay. All right, these also have some properties. The first is that it is going to preserve congruence. So, still going to be congruent. But in this one, the orientation of the figure can change. For example, if I was to reflect this pen across this line here, right now, the pen's pointing down, right? But if I reflected it, now the pen is pointing up. So it just changes its direction that it's facing. Okay, and then your line of reflection definition is that it's a perpendicular bisector of every segment that connects a point and its image. So the difference, I had someone ask me earlier, the difference between a bisector and a midpoint is just the point in the middle, right? A bisector is going to be a line that goes through the middle. All right, and then once you've got that, in the next section there are two examples and they want you to draw what the reflection for each of those would look like. So go ahead and give somewhat of a sketch there on what you think the reflection of both of those figures would look like across the lines of reflection that are drawn there for you. Okay, so for figure A, if I was to reflect that shape across, A and A prime should be directly across from each other, B and B prime directly across from each other, C and C prime directly across from each other. Right? You can see they drew these lines here to show that they are perpendicular, they do form that right angle. Alright, exact same thing on B, right? This one, I gotta remember that if this is the top corner and this is A, and I reflect it across, A is now the bottom corner, right? So whenever I draw the reflection there, D and C are right below, A and B were reflected all the way down. So remember, your orientation will change. It's not going to be the exact same shape, just move down, because that would have been just a translation. Okay? Alright, in the next section, they want you to just draw a line of symmetry on each of those figures where you could fold it in half, where it would be reflected if you folded it in half. So, some of those may have more lines of symmetry than others, but you're going to draw as many lines of symmetry as you can on each figure. On that first one, how many lines did you guys draw? Just one, right? We can only fold it down the middle and everything match up. If I tried to fold it across this way, this line would land on a point, so it wouldn't match there. Same this direction. If I folded it down, same thing. I can only fold this one in half. Okay. All right, what about B? How many lines did you guys draw? 2, very good. So that one I can go from point to point or point to point this way, and it'll match up. What about C? How many lines did we draw? 2 again, good. All right, and then what about D? Very good. So we can draw 1 through each point, right? So if I went down the middle, if I turn my paper, it's still the same star, right? I can turn it and it's going to look the exact same way. Okay? Alright, so once you have all your lines of symmetry drawn there, they then want us to draw the reflecting points on examples A and B here at the bottom of the page. If you're trying to count here, you just need to draw a line that goes through every point. Just draw one line that goes through every point, and that'll cover it. Again, not really sure what happened to my grid here. But for point A, if I graph 3, 5, I'd be somewhere up here, right? Okay, if I reflect that across the x-axis runs this way. If I reflect it from up here across that axis, it ends up down here, right? Where at? Where would its coordinate point be? 3, -5, right. So what's the only difference between these 2 points? The y, and what happened to it? Right, just became the opposite sign. So that should be true anytime you're reflecting across the x-axis. So what would b prime be? -2, -1. Very good. Okay. And then b is reflecting across the y-axis. So if I had some point -4, 2, and I reflect it across this line, where's it going to end up? 4, 2. So on that one, what changed? Right, the sign of x. Okay, so c prime would be +4, 2, which means d prime is going to be -3. Very good. Okay, so across the x changes your sign of y. Across y is going to change your sign of x. All right? Then go ahead and flip it on to that last page. Okay, on these, we're reflecting on I guess it's C on y'all, across the line y equals x. So that's this line right here, right? Okay, so that means if I had some point here, I'm going to reflect it across here, but then I also have to reflect it down. If I want it to go across this line, y equals x, I'm reflecting across and down, both. Okay? So that's not just going to be changing signs of things. It's going to put them in the exact opposite spot of where it currently is. So it's going to switch your x and y values. Okay? So if I switch 0 and 0, is that going to change anything? No. So m prime is still just going to be at 0, 0. Okay? But what about I prime? What's it going to become? Good. And what's L prime going to be? 3, 2. And K prime? Very good. Okay, so if we reflect across the line, y equals x, we're basically just switching our x and y. Okay? All right, and then last one, this one says to reflect it about the line y equals -x. So same line, but slants the other direction. So again, it's still going to switch them, but it's also probably going to be what's their signs, since this is negative. Switch the signs too. Okay? So I switched their places and their signs. So what is t prime going to be? 0, 3. What is I prime going to be? -2, 2. Right? And then A prime and N prime. Very good. Okay. All right, and then they made a little place for us to write down what we basically have just observed. So when we reflected across the x-axis, what did we say was going to happen? Right. So just changes y. When I reflect across the y-axis, it's going to change the x value, right? Just changes the sign. Okay, when I reflect about the line y equals x, what happens to our point? Flips. Good. And then when I reflect about the line y equals -x, right. So flips their places and makes them negative, or if they were negative, they become positive. All right. Good deal. When's the last time